I need to tell you something that might be difficult to hear. And believe me, as someone who has spent his entire career exploring the most exotic possibilities in physics, string theory, extra dimensions, the fabric of space-time itself, this is not something I say lightly. But I think it's important to be honest with you about where the physics actually leads. Warp drive will never work. Now, I know that's a bold statement. I know it sounds like the kind of thing scientists said about powered flight before the Wright brothers, or about breaking the sound barrier before Chuck Yeager. History is full of confident pronouncements about what's impossible that turned out to be wrong. So why am I willing to make such a definitive claim about warp drive? Because this isn't about engineering limitations. It's not about needing better materials or more powerful computers or some breakthrough we haven't thought of yet. The problems with warp drive are fundamental. They're woven into the basic structure of physics itself. And while I always want to remain open to surprises, science has certainly surprised us before, the obstacles here are so profound, so deeply rooted in our understanding of nature, that I think we need to be honest about what we're facing. But here's the thing, and this is important. Understanding why warp drive won't work turns out to be one of the most fascinating journeys you can take through modern physics. It touches on Einstein's relativity, quantum mechanics, the nature of energy and matter, causality itself. By the time we're done, you'll understand not just why this particular dream is likely impossible, but why the universe is structured in ways that make certain things genuinely, fundamentally off limits. So let me take you on that journey. Let's explore what warp drive is supposed to do, why it seemed like it might work, and why ultimately the universe says no. Let's start with the basic problem that warp drive is meant to solve: the tyranny of distance. You know, when you look up at the night sky, those points of light seem close. They're all right there, a few inches apart from your perspective, twinkling in the darkness. But that intimacy is an illusion created by the limitations of human perception. The actual distances involved are staggering beyond comprehension. The nearest star to our sun, Proxima Centauri, is about 4.24 light years away. Now, a light year sounds like it might be a unit of time, but it's actually a unit of distance. The distance light travels in 1 year, and light moves fast. About 186,000 miles per second. In 1 year, light covers roughly 5.88 trillion miles. So Proxima Centauri is about 25 trillion miles away. Let me try to put that in perspective. If you could drive to Proxima Centauri at highway speeds, let's say 60 miles per hour, which is about as fast as most of us ever travel on a regular basis, it would take you about 48 million years to get there. That's not a typo. 48 million years. That's longer than the entire history of primates on Earth. Okay, so cars are slow. What about our fastest spacecraft? The Parker Solar Probe, which is currently the fastest human-made object, reaches speeds of about 430,000 miles per hour when it's closest to the sun. At that speed, and this is an extraordinary speed by any human standard, it would still take about 6,600 years to reach Proxima Centauri. That's the nearest star. The galaxy is 100,000 light years across. The nearest large galaxy, Andromeda, is 2.5 million light years away. And the observable universe extends about 46 billion light years in every direction. The distances are not just large, they're fundamentally incompatible with human ambition if we're limited to conventional propulsion. Even at significant fractions of the speed of light, let's say 10% of light speed, which is vastly beyond our current capabilities, it would take over 40 years just to reach Proxima Centauri. A human lifetime for the nearest star, centuries or millennia for anything more distant. This is why science fiction invented warp drive. There had to be a way around the problem, a loophole in the cosmic speed limit that would let us explore the galaxy, meet alien civilizations, have adventures among the stars. Without some form of faster-than-light travel, space opera is impossible. The galaxy remains forever out of reach. And here's where things get interesting, because in 1994, a physicist named Miguel Alcubierre published a paper that seemed to offer exactly the loophole we needed. Alcubierre was working within the framework of general relativity, Einstein's theory of gravity, which describes gravity not as a force, but as the curvature of space-time caused by mass and energy. In general relativity, space-time isn't a fixed stage on which events play out. It's a dynamic entity that can bend, stretch, warp, and ripple. And Alcubierre realized something clever. Einstein's special relativity says that nothing can travel through space faster than light. But it doesn't say anything about space itself. Space can expand faster than light. In fact, it's doing so right now at the edges of the observable universe. Distant galaxies are receding from us faster than light, carried along by the expansion of space itself. So Alcubierre asked, what if you could create your own localized expansion and contraction of space? What if you could contract the space in front of your ship, essentially pulling your destination closer while expanding the space behind you, pushing your origin away? You'd be sitting in a bubble of flat space-time, not moving at all relative to your local space, while the bubble itself surfs through the universe at arbitrarily high speeds. This is the Alcubierre warp drive. And mathematically, within general relativity, it works. You can write down solutions to Einstein's field equations that describe exactly this kind of space-time geometry. The math is valid, the geometry is consistent. As a theoretical construct, it's perfectly sound. When Alcubierre published his paper, it caused a sensation. Here was a serious physicist using serious mathematics showing that faster-than-light travel was permitted by Einstein's own theory. It wasn't science fiction anymore, it was science fact, at least in principle. But, and here's where we need to pump the brakes, being mathematically possible is very different from being physically achievable. General relativity allows for many exotic space-time geometries. It allows for wormholes, for time machines, for closed time-like curves that loop back on themselves. The equations permit these things. But permitting something mathematically is not the same as saying it can exist in the real universe. And this is where the problems begin. Serious problems. Problems that, as we dig into them, reveal why the warp drive dream is almost certainly just that, a dream. Let me walk you through the first and most famous problem, exotic matter. To create an Alcubierre warp bubble, you don't just need energy. You need a very specific kind of energy, negative energy. And negative energy is, to put it mildly, problematic. Now, what do I mean by negative energy? In everyday experience, energy is always positive. A moving car has kinetic energy. A stretched spring has potential energy. A hot cup of coffee has thermal energy, all positive. Energy is the capacity to do work, to cause change, and it's always a positive quantity in classical physics. But in quantum mechanics, things get weird. There are certain situations where you can have regions of negative energy density, places where, in some sense, there's less than nothing. The most famous example is the Casimir effect. Here's how it works. Take two parallel metal plates and bring them very close together. We're talking microscopic distances, fractions of a micrometer. According to quantum mechanics, empty space isn't really empty. It's seething with virtual particles popping in and out of existence, creating what we call vacuum fluctuations. These fluctuations have energy. Now, between the plates, only certain wavelengths of vacuum fluctuations can fit the plates' imposed boundary conditions that exclude some modes. Outside the plates, all wavelengths are present. This creates an imbalance. There's more vacuum energy outside the plates than inside. The result is a tiny attractive force between the plates, the Casimir force, which has been measured experimentally. The region between the plates has lower energy density than the surrounding vacuum. In some technical sense, relative to the normal vacuum, it has negative energy density. This is encouraging for warp drive enthusiasts. It shows that negative energy isn't purely fictional. Quantum mechanics allows for it in certain configurations. Maybe we could engineer a system that produces enough negative energy to create a warp bubble. But here's the problem. The amounts involved in the Casimir effect are absolutely minuscule. We're talking about energy densities of perhaps 10 -4 joules per cubic meter. The original calculations for the Alcubierre drive suggested you'd need negative energy equivalent to the mass energy of Jupiter. Later, refinements brought that down somewhat. Some calculations suggested you might get away with only the mass energy of a few suns worth of negative matter. Let me put that in perspective. The most powerful nuclear weapon ever detonated, the Tsar Bomba, released about 2 × 10^17 joules. The mass energy of the sun is about 1.8 × 10^47 joules. That's 30 orders of magnitude difference. We're talking about energy scales that exceed anything humanity has ever contemplated by factors that make astronomical numbers look modest. And it's not just the amount of negative energy, it's that we have no idea how to produce macroscopic quantities of negative energy at all. The Casimir effect gives us tiny wisps confined to microscopic regions requiring precisely engineered boundary conditions. Scaling that up to propel a spacecraft is like trying to power a city with the static electricity from rubbing a balloon on your hair. Some physicists have explored whether modifications to the Alcubierre geometry might reduce the energy requirements, and there has been some progress. Certain configurations seem to require less exotic matter than others. But less is relative. Even the most optimistic scenarios require negative energy densities and quantities that are many, many orders of magnitude beyond anything we know how to produce. And here's a deeper issue. We don't actually know if negative energy can exist in bulk form at all. The Casimir effect and similar quantum phenomena produce negative energy densities in bounded regions sandwiched between regions of positive energy. The total energy is always positive or zero. Quantum mechanics seems to have built-in constraints, sometimes called quantum inequalities, that limit how much negative energy you can have in any given region and for how long. These quantum inequalities suggest that the universe has a kind of cosmic censorship that prevents negative energy from accumulating in ways that would allow exotic space-time geometries like warp bubbles or traversable wormholes. The math of general relativity might allow these things, but the quantum rules that actually govern matter and energy might forbid them. So that's problem one, exotic matter. We need something that might not be able to exist in quantities that dwarf anything we can imagine producing. Not a great start. But let's press on, because even if we could somehow solve the exotic matter problem, there are more obstacles ahead. Let me tell you about problem 2, the horizon problem. Imagine you've somehow acquired your negative energy, maybe alien benefactors gave it to you, maybe you found a cosmic cheat code, whatever. You construct your warp bubble and prepare to engage the drive. What happens? Well, here's something that wasn't obvious in Alcubierre's original paper, but became clear in subsequent analysis. The warp bubble, once it's traveling faster than light, cannot be controlled from inside. Think about why. You're inside the bubble in a region of flat space-time. The bubble wall is moving faster than light relative to the space outside. Any signal you try to send to the bubble wall to steer, to slow down, to do anything can only travel at the speed of light at most. But the bubble wall is receding from you faster than light can catch up. Your commands can never reach it. This is called the horizon problem, by analogy to the event horizon of a black hole. Once you're inside the bubble and it's at superluminal speed, you're causally disconnected from the bubble wall. You're a passenger with no control, hurtling through the universe in a direction and at a speed you cannot influence. How do you stop? You can't send a stop signal to the front of the bubble. How do you steer? You can't send navigation commands to the bubble wall. The very superluminal speeds that make warp drive attractive also make it uncontrollable. Some researchers have suggested you might pre-program the bubble's trajectory before engaging, setting up the geometry in advance so it naturally slows down or changes direction at the right points. But this requires knowing exactly where you want to go before you leave, with no possibility of course correction. Hit an unexpected obstacle? Too bad. Destination moved? Too bad. Any change in plans requires you to somehow decelerate to subluminal speeds, at which point the whole point of the drive is defeated, make your changes, and then reaccelerate. And the deceleration itself is problematic. How do you slow down a warp bubble from inside when you can't communicate with the bubble wall? You'd need to have set up the deceleration in advance, which means the entire trajectory, including the endpoint, must be determined before departure. This isn't a spacecraft, it's a bullet. Once fired, it goes where it goes. Maybe you're thinking, okay, that's inconvenient, but it's an engineering problem, not a fundamental physics problem. If we can create the bubble at all, maybe we can create it with the right pre-programmed trajectory, annoying, but workable. But the horizon problem points to something deeper, which brings us to problem 3, causality violation. This one is serious, maybe the most serious of all. You see, special relativity doesn't just tell us that nothing can travel faster than light. It tells us why. Because faster than light travel would allow causality violation. You could, in principle, send information into your own past. You could create paradoxes where effects precede causes. The logical structure of the universe would break down. Let me explain how this works. In special relativity, different observers moving at different speeds disagree about the timing of distant events. This is called the relativity of simultaneity, and it's one of the most counterintuitive aspects of Einstein's theory. Imagine two events, A and B, happening at different locations. For an observer at rest, relative to these events, they might happen at the same time. They're simultaneous. But for an observer moving relative to the first, these events are not simultaneous. One happens before the other. And for an observer moving in the opposite direction, the order is reversed. The other one happens first. This is weird, but it's not paradoxical as long as the events are space-like separated, meaning no light signal or anything traveling at or below light speed could connect them. If A can't influence B and B can't influence A, then it doesn't really matter that observers disagree about which happened first. There's no causal relationship to get confused about. But what if you could send a signal faster than light? Then events that are space-like separated could be causally connected. And now the relativity of simultaneity becomes a problem. Here's a thought experiment. Alice and Bob are at rest relative to each other, separated by some distance. Alice sends a faster than light signal to Bob. From Alice's perspective, she sends at time t1 and Bob receives at time t2, where t2 is slightly later than t1. The signal traveled into her future. But now consider Carol, who is moving relative to Alice and Bob. Because of the relativity of simultaneity, Carol might see the events in a different order. In her reference frame, Bob might receive the signal before Alice sends it. The signal traveled into her past. By itself, this is strange but not yet paradoxical. But now suppose Bob immediately sends a faster-than-light reply to Alice. In Carol's frame, this reply might arrive at Alice before Alice sent her original message. And if we're clever about the relative velocities and the distances, we can arrange for Alice to receive Bob's reply before she sends her original message. She gets a message from the future. She could receive instructions not to send the original message. Paradox, causality violation. The logical structure of events collapses. This isn't just a quirk of the Alcubierre drive. It's a general consequence of any form of faster-than-light travel or communication within the framework of special relativity. FTL implies time travel, implies paradox. Now, you might object, the Alcubierre drive doesn't really go faster than light. The ship inside the bubble is stationary relative to its local space. It's the bubble itself that moves superluminally. Doesn't that avoid the problem? Unfortunately, no. The causality violation doesn't depend on the mechanism of superluminal travel. It depends only on the fact that you can get from point A to point B faster than light could. If you can do that by warp drive, by wormhole, by teleportation, by any means whatsoever, then you can construct scenarios where effects precede causes. The Alcubierre drive is a superluminal transportation system. It gets you somewhere faster than light would. That's the whole point. And that means it shares the causality problems of all superluminal travel. Some physicists have tried to argue around this. Maybe causality violation only seems paradoxical because of how we think about it. Maybe the universe has some self-consistency principle that prevents actual paradoxes from occurring any time loop that would create a contradiction, somehow cancels itself out. This is the approach taken in some interpretations of closed time-like curves. You can have time travel, but only if everything is consistent. No killing your grandfather, no changing the past in ways that contradict the present. Physics somehow conspires to prevent paradoxes. But even if this works, and it's far from clear that it does, it leads to bizarre consequences. Free will becomes questionable if your actions are constrained by the need for self-consistency. The universe starts to feel less like a place where things happen and more like a solved equation where every variable was determined from the beginning. Most physicists, when confronted with these implications, conclude that nature probably just forbids superluminal travel outright. The causality problems aren't bugs in our analysis. They're the universe's way of saying, this is not allowed. And this brings me to something deeper, something I think about a lot. You know, physics isn't just a collection of equations. It's a description of how reality works, of what's possible and what isn't. And the laws of physics aren't arbitrary. They're not like traffic laws that someone made up and could change if they wanted. They're features of the universe itself woven into the fabric of space-time. The speed of light as a cosmic speed limit isn't a design flaw or an obstacle to be overcome. It's a fundamental aspect of how space-time is structured. Special relativity tells us that space and time are unified into a four-dimensional continuum. and the speed of light defines how those dimensions relate to each other. Breaking the light barrier isn't like breaking the sound barrier. It's not a matter of having enough energy or the right technology. It's more like asking to travel north of the North Pole. The request doesn't make sense given the structure of the thing you're asking about. I know that's a disappointing message for those of us who grew up on Star Trek and Star Wars, who dreamed of zipping between the stars at warp speed. I feel that disappointment too. But I think there's something valuable in accepting it, in understanding why the universe is the way it is, rather than wishing it were different. And here's the thing, even without warp drive, the universe is astonishing. It's vast, beyond comprehension, filled with wonders we've barely begun to explore. The constraints of light speed mean we'll never have a galactic empire, never meet aliens in distant star systems, never see the far reaches of the cosmos in person. But within those constraints, there's still a solar system to explore, still the possibility of reaching nearby stars over generational timescales, still the joy of understanding our place in the cosmos through observation and theory. The universe didn't owe us interstellar travel. It gave us enough a planet teeming with life, a solar system rich with resources, a window onto a cosmos that stretches billions of light years in every direction. If we can't have everything, that doesn't mean we have nothing. But I'm getting ahead of myself. We've covered exotic matter, the horizon problem, and causality violation. And we're just getting started, because there are more problems with warp drive, problems that dig even deeper into the structure of physics, problems that I think are even more decisive than the ones I've described. In our next part, I want to take you through the energetic catastrophe at the bubble wall, the problems with creating the bubble in the first place, what quantum mechanics has to say about all of this, and why even sympathetic physicists who've worked on these ideas for decades have largely concluded that the dream is unachievable. The story of warp drive is, in many ways, the story of physics itself, a story of beautiful ideas constrained by harsh realities of mathematical possibilities that nature refuses to permit. Understanding why warp drive fails teaches us something profound about the universe we actually live in. So we'd arrived at this sobering point where the Alcubierre warp drive faces three fundamental obstacles: the need for exotic matter in quantities we can't imagine producing, the horizon problem that makes the bubble uncontrollable from inside, and the causality violations that seem to follow inevitably from any form of faster-than-light travel. Now, you might be thinking, and this is a reasonable thought, that maybe these problems could be solved with enough ingenuity. Maybe we'll discover new physics that allows for exotic matter production. Maybe we'll find clever workarounds for the control problem. Maybe the causality issues aren't as fatal as they seem. I want to take those hopes seriously. I want to examine what the physics actually says, not just wave my hands and declare things impossible. So let me take you deeper into the problems, because honestly, the more you dig, the worse it gets. Let's talk about what I call the energetic catastrophe at the bubble wall. You know, when Alcubierre first proposed his metric, the focus was on whether the geometry was mathematically consistent with general relativity, and it was the math checks out. But math and physics aren't the same thing. You can write down equations that are internally consistent but describe situations that could never actually occur. One of the things that became clear in subsequent analysis is that the warp bubble, if it existed, would have some truly horrifying properties. Consider what happens at the bubble wall, the boundary between the contracted space ahead and the expanded space behind. This is where all the exotic matter would need to be concentrated, forming a thin shell around the flat space-time region where your ship sits. Now, as the bubble moves through space, it's interacting with everything in its path. Particles, photons, cosmic dust, all the stuff that fills what we think of as empty space. And here's the thing. When these particles hit the bubble wall, they don't just pass through peacefully. They get caught up in the extreme space-time curvature of the bubble boundary. A paper published by physicists Stefano Finazzi, Stefano Liberati, and Carlos Barcelo in 2009 analyzed this in detail, and what they found was disturbing. Particles that encounter the bubble wall get blue shifted. Their energy increases dramatically as they interact with the warped space-time, and they accumulate at the front of the bubble. By the time you arrive at your destination and the bubble dissipates, all that accumulated energy gets released. It's not a gentle arrival. It's a catastrophic burst of high-energy particles, essentially a weapon of mass destruction aimed at wherever you're going. The calculations suggested that even a relatively modest warp trip could release enough energy to devastate entire planets. You wouldn't be exploring the galaxy, you'd be sterilizing it. Now, maybe you're thinking, okay, that's bad, but it's an engineering problem. Maybe we can design the bubble to dissipate gradually, or aim it away from inhabited areas, or find some way to bleed off the accumulated energy safely. But here's the thing, this isn't really an engineering problem. It's a consequence of the fundamental physics of how the bubble interacts with the matter and radiation that fills space. You can't have a superluminal warp bubble that doesn't do this. The energy accumulation follows directly from the space-time geometry. And it gets worse when you consider quantum effects. In quantum field theory, space-time curvature affects the vacuum, the quantum fields that permeate all of space. Strong curvature, like you'd have at the bubble wall, can cause vacuum instabilities. Particle-antiparticle pairs that would normally flicker in and out of existence too quickly to notice get torn apart by the space-time geometry. Virtual particles become real particles. This is similar to what happens near a black hole. It's the mechanism behind Hawking radiation. But at a warp bubble wall, the effect could be dramatically more severe. Some analyses suggest the bubble would radiate intensely, losing energy catastrophically. Others suggest it would generate runaway instabilities that would cause the bubble to collapse or explode. The details are still debated because the calculations are difficult. You're dealing with quantum field theory in curved space-time, which is notoriously challenging. But the general conclusion from most researchers who've studied this is that warp bubbles would be quantum mechanically unstable. They wouldn't just be hard to create, they'd be impossible to maintain. Let me put this in perspective. We have a space-time geometry that requires exotic matter we can't produce, that would be uncontrollable once activated, that might violate causality, that would devastate anything at its destination, and that would probably be quantum mechanically unstable anyway. At some point, you have to step back and ask, is the universe trying to tell us something? I think it is. I think all of these problems, which emerge from different aspects of physics, from different analyses, from different researchers, are pointing toward a unified conclusion. This isn't allowed. The universe has multiple overlapping mechanisms that prevent warp drive from being possible. It's not one obstacle we need to overcome. It's a whole fortress of obstacles, each reinforcing the others. But let's keep going, because I promise to be thorough. Let me tell you about another problem that I find particularly compelling, the creation problem. Suppose you've somehow solved all the issues I've mentioned so far. You've got your exotic matter. You've figured out how to control the bubble. You've found a way to arrive without destroying your destination. You've stabilized the quantum fluctuations. You're ready to go. How do you actually create the bubble in the first place? Here's the issue. The Alcubierre metric describes a warp bubble that already exists and is already moving. It doesn't tell you how to create one from scratch. And when you try to figure out the creation process, you run into a fundamental chicken and egg problem. To create the bubble, you need to arrange exotic matter in a specific configuration around your ship. But to arrange that exotic matter, you need to move it into position, and moving exotic matter, assuming it exists, requires time. The arrangement process is limited by the speed of light, just like everything else. Here's what that means in practice. Suppose you want to create a warp bubble that will take you to Alpha Centauri 4.24 light years away. Before you can start your journey, you need to set up the exotic matter configuration. That configuration extends in the direction of travel, and setting it up requires sending exotic matter to the appropriate locations ahead of you. But you can't send anything faster than light. So setting up the bubble configuration for a journey to Alpha Centauri requires at least 4.24 years, the time for light to travel there and back. And by the time you've set up the bubble, you might as well have just traveled there conventionally. This is a subtle but devastating problem. The warp bubble doesn't help you get somewhere faster than light if creating the bubble requires sending information or matter there first at light speed. It's like building a bridge by first swimming to the other side. By the time the bridge is ready, you've already made the journey. Some researchers have suggested you might create a series of relay stations, pre-positioned exotic matter caches that you could activate remotely to set up bubble segments ahead of you. But this still requires the relay stations to be placed in advance at subluminal speeds. You'd need to have already colonized the destination region before you could warp there. It's a bootstrap problem. To benefit from warp drive, you need infrastructure that can only be created without warp drive. The technology doesn't help you do anything you couldn't already do. Now, I've been focusing on the Alcubierre drive specifically, but I want to step back and talk about the broader picture. Because the Alcubierre drive isn't the only proposed mechanism for faster than light travel. There are others: wormholes, Krasnikov tubes, various modifications to the basic Alcubierre idea, and they all face similar problems. Let me tell you about wormholes, because they're probably the most famous alternative. A wormhole is a hypothetical tunnel through space-time connecting two distant points. Instead of traveling through normal space from A to B, you take a shortcut through the wormhole. The distance through the wormhole might be much shorter than the distance through normal space, allowing you to arrive at distant locations quickly. Wormholes emerge naturally from the mathematics of general relativity. The simplest wormhole solution is the Einstein-Rosen bridge, discovered in 1935 by Albert Einstein and Nathan Rosen. It connects two black holes. You enter one black hole, travel through the wormhole, and exit from the other. The problem is that Einstein-Rosen bridges are not traversable. They form and collapse too quickly for anything to pass through. You'd be crushed by the singularity before you completed the journey. In 1988, physicists Kip Thorne and Michael Morse asked whether there could be stable, traversable wormholes, wormholes you could actually use for transportation. They found that the answer is yes, mathematically speaking, but only if the wormhole is threaded with exotic matter. The same exotic matter we need for the Alcubierre drive, negative energy density, violating the energy conditions that normal matter satisfies. So we're back to the same fundamental problem. Traversable wormholes require exotic matter. We don't know if exotic matter can exist in the required form. And all the issues I mentioned earlier, causality violation, quantum instability, the difficulty of creating and controlling such structures, apply to wormholes too. Moreover, wormholes have their own additional problems. To use a wormhole for transportation, you need to already have the two ends positioned at the origin and destination. How did they get there? Somebody had to move them there. And moving wormhole mouths around is subject to the same light speed limitations as everything else. There's a famous thought experiment that illustrates this. Suppose you have a wormhole with both mouths starting on Earth. You put one mouth on a spaceship and accelerate it to near light speed, then bring it back. Because of time dilation, time passes more slowly for the traveling mouth. When you reunite the mouths, they're no longer synchronized. You could potentially walk through the wormhole and emerge before you left. This sounds like you've created a time machine. But look at what it required. You had to accelerate a wormhole mouth to near light speed and bring it back. That takes enormous energy and, crucially, takes time, normal, subliminal time. You haven't escaped the light speed barrier. You've just created a weird temporal shortcut that still required a subliminal journey to set up. And of course, if wormholes allow time travel, they inherit all the causality problems we discussed earlier. Paradoxes, self-consistency constraints, the breakdown of physical predictability. The pattern keeps repeating. Every proposed faster-than-light mechanism runs into the same fundamental obstacles: exotic matter, causality violation, creation problems, quantum instability. It's as if the universe has multiple layers of defense against superluminal travel, each backing up the others. Let me take you now into what might be the deepest level of this defense, what quantum gravity has to say about all of this. You know, general relativity and quantum mechanics are our two most successful physical theories. General relativity describes gravity and space-time at large scales, planets, stars, galaxies, the cosmos. Quantum mechanics describes matter and energy at small scales, atoms, particles, fields. Both theories are extraordinarily accurate within their domains. But we know they can't both be complete because they're fundamentally incompatible. General relativity treats space-time as smooth and continuous. Quantum mechanics suggests everything is ultimately discrete and probabilistic. When you try to apply both theories to the same situation, like the interior of a black hole or the first moments of the Big Bang, you get nonsense, infinities and contradictions. The quest for a quantum theory of gravity, a framework that unifies general relativity and quantum mechanics, has been one of the great challenges of theoretical physics for nearly a century. We don't have a complete theory yet, but we have candidates: string theory, loop quantum gravity, various other approaches. And here's what's interesting. Most approaches to quantum gravity suggest that the exotic space-time structures needed for warp drives and wormholes might be forbidden at a fundamental level. In string theory, for example, there's something called the chronology protection conjecture proposed by Stephen Hawking. Hawking noticed that whenever you try to create a time machine in general relativity, which would be possible if you could build a warp drive or traversable wormhole, quantum effects seem to conspire to prevent it. Vacuum fluctuations build up at the would-be time machine, creating divergent energy densities that destroy the structure before it can become a time machine. Hawking proposed that this might be a general feature of nature. The laws of physics prevent the formation of closed time-like curves no matter what you do. The universe protects causality. We don't have proof of the chronology protection conjecture that would require a complete theory of quantum gravity, which we don't have. But the evidence from multiple partial calculations points in that direction. Whenever you approach the conditions needed for time travel, which includes faster than light travel, quantum effects seem to blow up and block you. Loop quantum gravity, another approach to quantum gravity, has similar implications. In loop quantum gravity, space-time is fundamentally discrete at extremely small scales, around 10 negative 35 meters, the Planck length. Smooth space-time is an approximation that emerges at larger scales, like how a smooth fabric emerges from individual threads. At the quantum level, there might not be room for the exotic space-time configurations needed for warp drives. The discrete structure might simply not permit the kinds of extreme curvature and topology required. It would be like trying to tie a knot in a fabric where the threads are too coarse, the structure doesn't support it. These are speculative ideas because we don't have a complete theory of quantum gravity. But they point in a consistent direction. The exotic spacetimes that would allow faster than light travel might not be possible once you fully account for quantum effects. And there's a philosophical argument here too, though I want to be careful because philosophy isn't physics. If faster than light travel is possible, then time travel is possible. If time travel is possible, then causality, the principle that causes precede effects, is violated. And without causality, it's hard to see how science itself can work. Science depends on the idea that we can do experiments, observe results, and infer laws. But if effects can precede causes, then experimental results might not have consistent explanations. The future might influence the past in ways that make the whole enterprise of understanding nature incoherent. This isn't a proof that faster than light travel is impossible, but it's suggestive. The logical structure of science, the coherence of physical explanation, seems to depend on causality. And causality seems to depend on the light speed limit. It's all connected. Now, I want to address something that I know some of you are thinking. Brian, you're being too pessimistic. Science has been wrong before. We used to think atoms were indivisible. We used to think the universe was static. We used to think powered flight was impossible. Every generation has its confident pronouncements about what can't be done, and every generation gets proven wrong. I take this objection seriously. I really do. The history of science is full of overconfident skeptics who are subsequently embarrassed, and I never want to be in the position of stifling inquiry by declaring something impossible. But I think there's a crucial distinction to make. The things we used to think were impossible, powered flight, atomic energy, breaking the sound barrier, were engineering challenges. They pushed against the limits of our technology, not the limits of physics. There was nothing in the fundamental laws of nature that forbade airplanes or nuclear reactors. We just didn't know how to build them yet. The light speed limit is different. It's not an engineering challenge. It's a structural feature of space-time itself. Overcoming it isn't like building a better engine. It's like finding a direction north of the North Pole. The request doesn't make sense given the nature of what's being asked about. Moreover, the history of science, while full of surprises, shows a consistent pattern. When we discover new physics, it doesn't invalidate the old physics in its domain of applicability. Quantum mechanics didn't show that classical mechanics was wrong. It showed that classical mechanics is an approximation valid at large scales. General relativity didn't show that Newtonian gravity was wrong. It showed that Newtonian gravity is an approximation valid at low speeds and weak fields. Whatever new physics we discover, it will have to reduce to special relativity in the appropriate limit. It will have to reproduce all the successful predictions of relativity, time dilation, length contraction, the invariance of the speed of light. These aren't provisional ideas that might be overturned. They're backed by countless experiments and built into the functioning of technologies we use every day. GPS satellites, for example, have to correct for both special and general relativistic effects. Without those corrections, the system would drift by kilometers per day. Particle accelerators rely on special relativity. The particles we accelerate behave exactly as relativity predicts. Every prediction we've tested has been confirmed. Could there be new physics beyond relativity? Of course. There almost certainly is. Quantum gravity, whatever it turns out to be, will go beyond general relativity, but it will incorporate relativity as a limit just as relativity incorporates Newtonian mechanics. The light speed limit isn't going away. It's too deeply woven into the fabric of reality. So when I say warp drive will never work, I'm not saying it with the casual confidence of a Victorian scientist declaring heavier than air flight impossible. I'm saying it based on a deep understanding of what the light speed limit actually is and why it exists. It's not a practical barrier, it's a fundamental feature of space-time geometry. And there's no known physics, no proposed physics, no coherent conceptual framework that allows for getting around it. But let me be clear about what I'm not saying. I'm not saying interstellar travel is impossible. It's possible, just slow. At significant fractions of the speed of light, which might be achievable with advanced propulsion systems like nuclear pulse drives or laser sails, travel to nearby stars could take decades rather than millennia. It's a far cry from warp speed, but it's something. I'm also not saying we'll never find anything surprising about space-time. We might. The universe has surprised us before and will probably surprise us again. But I'd be willing to bet that whatever we find won't include a loophole that allows faster than light travel. The constraints are too deep, too interconnected, too fundamental. And I'm not saying this makes the universe less interesting. On the contrary, understanding why certain things are impossible can be just as illuminating as understanding how things work. The light speed limit tells us something profound about the structure of reality. It's not a limitation to resent. It's a feature to understand and appreciate. Now, I want to spend some time on a question that I think is important. Given all these problems, why do physicists keep working on warp drive at all? It's a fair question. If the obstacles are as fundamental as I've described, why do papers keep getting published? Why do serious researchers devote time to this topic? The answer, I think, is that working on impossible things can still be valuable, even if warp drive can't be built. Studying it teaches us about physics. The Alcubierre metric is a legitimate solution to Einstein's equations, and understanding why it can't be physically realized tells us something about the relationship between mathematics and reality. It's like studying perpetual motion machines. We know they can't work, thermodynamics forbids them. But analyzing proposed perpetual motion designs helps us understand thermodynamics better. The impossibility is instructive. Similarly, analyzing warp drives helps us understand general relativity, quantum field theory, in curved space-time, the energy conditions, and the connections between faster-than-light travel and causality. It's a useful playground for exploring deep physics, even if the playground equipment can never be built. There's also the value of being precise about what's impossible and why. Saying warp drive won't work isn't very helpful if you can't explain the specific mechanisms that prevent it. Working out the details, the exotic matter requirements, the horizon problems, the quantum instabilities gives us a clear understanding of where the boundaries are. It maps the territory of the possible. And who knows? Maybe in mapping those boundaries, someone will find something unexpected. Maybe the analysis will reveal new physics, not faster than light travel per se, but something else we hadn't anticipated. Science often works that way. You set out to understand one thing and discover something completely different. So I don't begrudge the researchers who work on warp drive. They're doing legitimate physics, even if the ultimate goal is unachievable. What I do think is important is to be honest about the odds. Don't sell the public on the promise of interstellar travel by warp drive when the physics makes it overwhelmingly unlikely. Don't pretend the obstacles are just engineering challenges that will be overcome with enough funding and clever people. The universe has limits. Understanding those limits is part of understanding the universe. And accepting those limits isn't defeatism, it's maturity. In our final part, I want to pull all of this together. I want to talk about what the impossibility of warp drive means for humanity's future in space, what alternatives we actually have for reaching the stars, and how we should think about our place in a cosmos that seems determined to keep its distances vast and its travel times long. Because here's the thing, the universe didn't give us warp drive, but it gave us something else. It gave us minds that can understand why warp drive is impossible. It gave us the ability to comprehend space-time, to grasp the structure of reality, to ask questions that no other known species has ever asked. That's not nothing. That's not a consolation prize. That's the main event. The universe is knowable even if it's not traversable. And knowing the universe, truly understanding it, might be the greatest adventure of all. So we've journeyed through the physics of warp drive, the exotic matter requirements, the horizon problems, the causality violations, the energetic catastrophe at the bubble wall, the quantum instabilities, the creation paradoxes. We've seen how every proposed mechanism for faster-than-light travel runs into fundamental obstacles, not engineering challenges, but deep features of how the universe is structured. Now I want to step back and ask, what does this mean? What does it mean for our dreams of exploring the cosmos, for our hopes of meeting other civilizations, for our understanding of our place in the universe? Because I think the impossibility of warp drive isn't just a technical conclusion, it's a philosophical one. It tells us something profound about the nature of reality and our relationship to it. Let me start with something that might seem obvious, but I think is worth stating explicitly. The universe doesn't owe us anything. You know, when we watch science fiction, when we dream about the future, there's an implicit assumption that the universe will cooperate with our ambitions. We want to explore the galaxy, so there must be a way to do it. We want to meet aliens, so faster-than-light travel must be possible. Our desires shape our expectations of what physics will allow, but physics doesn't care about our desires. The laws of nature are what they are, regardless of what we want them to be. The universe wasn't designed for our convenience. It wasn't designed at all. It simply exists with its particular structure, its particular constraints, its particular possibilities. And one of those constraints is the speed of light, not as a practical limitation that sufficiently advanced technology might overcome, but as a fundamental feature of space-time geometry. The light speed limit isn't like a wall that could in principle be tunneled through or climbed over. It's more like the fact that you can't go north from the North Pole. It's not that something is blocking you. It's that the request doesn't make sense given the structure of the space you're in. I know this is disappointing. Believe me, I feel it too. I grew up on the same science fiction you did, dreaming of starships and alien encounters and galactic civilizations. The idea that we're confined to our cosmic neighborhood, that the stars will forever remain tantalizingly out of reach, that we'll never zip across the galaxy like Captain Kirk or Han Solo, it's a loss. A genuine loss of possibility. But I think there's something important to be said for accepting reality as it is, rather than as we wish it were. And I think that acceptance, far from being defeatist, opens up new ways of thinking about our situation that are ultimately more meaningful. Let me explain what I mean. When you accept that faster-than-light travel is impossible, you're forced to confront the actual situation. The stars are far away. Interstellar distances are measured in light years. Travel times, even at a significant fraction of light speed, would be measured in decades or centuries. The galaxy is vast, ancient, and largely empty. We are, for all practical purposes, alone in our little corner of the cosmos. That's the reality. And once you accept it, you can start asking more interesting questions. Not how do we overcome the speed limit, but how do we live meaningfully within it? Not how do we escape our cosmic isolation, but what does that isolation tell us about who we are? These are the questions I find genuinely compelling. Not because they're easier, they're not, but because they're grounded in reality. They're about the universe we actually live in, not the universe we wish we lived in. So let me talk about what's actually possible for interstellar travel, given the constraints of physics. The first thing to note is that interstellar travel is not impossible, it's just slow. The speed of light isn't a barrier to reaching other stars, it's a constraint on how quickly you can get there. And there's a big difference between slow and impossible. Right now, our fastest spacecraft, Voyager 1, launched in 1977, is traveling at about 38,000 miles per hour relative to the Sun. At that speed, it would take about 73,000 years to reach Proxima Centauri. That's too slow for practical interstellar exploration. But we can do better. Nuclear pulse propulsion, using nuclear explosions to push a spacecraft, could potentially achieve speeds of 5 to 10% of light speed. At 10% of light speed, the trip to Proxima Centauri would take about 43 years. That's a human lifetime, but it's conceivable. Laser sail propulsion, where powerful lasers on Earth push against a reflective sail attached to a small spacecraft, could achieve even higher speeds for small payloads. The Breakthrough Starshot Initiative is exploring this concept, aiming to send gram-scale probes to Proxima Centauri at 20% of light speed, arriving in about 20 years. These aren't warp drive, they don't get you to Alpha Centauri in time for lunch, but they're real physics, grounded in principles we understand and technologies we could plausibly develop. They represent what's actually possible. And here's something interesting. Even without faster than light travel, relativistic time dilation offers a kind of partial compensation. You know, one of the consequences of special relativity is that time passes more slowly for objects moving at high speeds. This is called time dilation, and it's not a theoretical speculation. It's been measured precisely in particle accelerators and with atomic clocks on airplanes and satellites. For a spacecraft traveling at 99% of the speed of light, time would pass about 7 times more slowly on the ship than for observers on Earth. At 99.9% of light speed, the factor is about 22. At 99.99%, it's about 70. What this means is that for the travelers themselves, interstellar journeys could be surprisingly short. A trip to a star 100 light years away at 99.9% of light speed would take about 100 years from Earth's perspective, but only about 4.5 years from the traveler's perspective. In principle, you could cross the entire galaxy 100,000 light years in a human lifetime as long as you were willing to accelerate to extreme velocities. The catch, of course, is that everyone you left behind would be dead when you arrived. You'd be traveling into the future, not just across space. This is a strange kind of interstellar travel, quite different from science fiction's casual zipping between star systems. But it's what physics actually allows. And there's something poetic about it, the universe saying, you can go far, but you can't come home. Generation ships are another possibility. Instead of trying to make the journey fast, you make it multi-generational. Build a large, self-sustaining habitat, fill it with a diverse population, and let them live, reproduce, and die during the centuries-long voyage The people who arrive at the destination would be the distant descendants of those who left. This raises fascinating questions about culture, identity, and continuity. Would the arriving population still consider themselves connected to Earth? Would they preserve knowledge and traditions across dozens of generations? Would they evolve culturally or even biologically into something quite different from their ancestors? Generation shifts are speculative, but they're not physically impossible. They're engineering challenges of immense scale, requiring technologies we don't yet have, but they don't violate any laws of physics. They're within the realm of the conceivable. And then there's the possibility that we might not need to send humans at all. Robotic probes, artificial intelligences, digital uploads of human minds, these could potentially make interstellar journeys that biological humans couldn't survive. A robot doesn't care if the trip takes 1,000 years. A digital mind could be paused for the journey and resumed on arrival. This opens up a different kind of interstellar exploration, one where the explorers aren't biological beings in the traditional sense, but are technological descendants or digital representatives. It's not the Star Trek future, but it might be a future nonetheless. Now, I want to address something that I think is important, the question of meaning. You know, when people are disappointed by the impossibility of warp drive, it's not just about transportation. It's about what interstellar travel represents, the expansion of human horizons, the encounter with the alien and unknown, the sense of boundless possibility. Warp drive isn't just a technology. It's a symbol of transcendence, of humanity's ability to overcome any limitation. And I understand that. I feel it too. The idea that we might be forever confined to a tiny bubble in an infinite cosmos is, in some sense, deflating. It makes us feel small, limited, trapped. But here's another way to think about it. The universe is 93 billion light years across. It contains roughly 200 billion galaxies, each with hundreds of billions of stars. There are more stars in the observable universe than grains of sand on all the beaches of Earth. The cosmic story spans 13.8 billion years and will continue for trillions more, and we tiny creatures on a tiny planet around an ordinary star have figured out how it works. We've deduced the laws that govern everything from subatomic particles to galaxy clusters. We've traced the history of the universe from the first fraction of a second after the Big Bang to the present day. We've predicted phenomena decades before we observe them, and our predictions have been confirmed with staggering precision. That's not nothing. That's remarkable. We may not be able to travel to distant stars, but we can understand them. We can analyze their light, determine their composition, measure their distances, map their motions. We can study exoplanets and search for signs of life. We can probe the cosmic microwave background and glimpse the universe when it was only 380,000 years old. The universe is knowable, even if it's not traversable. And knowing it, truly understanding it, is its own form of transcendence. I sometimes think about the ancient astronomers, Babylonians, Greeks, Mayans, who studied the stars with nothing but their eyes and their minds. They couldn't travel to the moon, much less the planets or stars. But they tracked the motions, identified patterns, built mathematical models. They reached out with their intellects, even though their bodies were confined to Earth. We're doing the same thing, just with far more powerful tools. Our telescopes see galaxies billions of light years away. Our particle accelerators recreate conditions from the first moments of the universe. Our mathematical theories probe realms that no human will ever visit the interior of black holes, the first Planck time after the Big Bang, the hypothetical multiverse. We are explorers, just not physical explorers, in the way science fiction imagined. We're intellectual explorers, using the power of human understanding to reach places our bodies never could. And I think that's enough. I really do. Not because physical exploration wouldn't be wonderful, it would be, but because intellectual exploration is wonderful too. The universe gave us minds that can comprehend it. That's a gift. That's a privilege. That's something to celebrate. Let me talk about something else that I think the impossibility of warp drive teaches us: humility. You know, humanity has a tendency toward grandiosity. We like to think of ourselves as destined for greatness, as the inevitable masters of nature, as the species that will spread across the galaxy and perhaps one day the universe. Science fiction feeds this narrative. We're always the heroes, always overcoming obstacles, always achieving our cosmic destiny. But the universe isn't a story with humanity as the protagonist. It's a vast, indifferent, largely empty space governed by impersonal laws. We emerged from it from the same atoms that make up stars and planets, forged in the nuclear furnaces of ancient suns, but we're not its purpose or its center. We're a temporary arrangement of matter that happens to be capable of understanding its own origins. The impossibility of warp drive is a reminder of this. We don't get to rewrite the laws of physics to suit our ambitions. We have to work within the constraints that nature provides. And those constraints are real, immovable, non-negotiable. I don't think this is depressing. I think it's clarifying. It helps us see ourselves more accurately, not as the destined conquerors of the cosmos, but as curious, clever, limited creatures trying to make sense of an incomprehensibly vast universe. And from that clearer vision, I think, comes a more appropriate response to our situation. Not frustration at constraints we can't overcome, but appreciation for what we can do. Not resentment at the universe's indifference, but wonder at its existence. Not entitlement to interstellar travel, but gratitude for the stars we can see and the physics we can understand. Now, I want to address something that some of you might be thinking. What about exotic physics? What about things we haven't discovered yet? Isn't it arrogant to declare warp drive impossible when we don't have a complete theory of everything? It's a fair question, and I want to take it seriously. You're right that our physics is incomplete. We don't have a quantum theory of gravity. We don't fully understand dark matter or dark energy. There might be aspects of reality we haven't glimpsed yet, phenomena that would seem as strange to us as quantum mechanics would seem to Newton. And I acknowledge that in principle, something could be hiding in those unexplored regions that would change the picture. I can't prove with absolute certainty that faster than light travel is impossible. I can only tell you that everything we know points strongly in that direction. But here's the thing. Humility cuts both ways. Yes, we should be humble about the limits of our knowledge. We should remain open to surprises. But we should also be humble about our hopes and desires. Just because we want faster than light travel doesn't mean the universe will provide it. The history of physics shows a consistent pattern. When new theories emerge, they don't overturn the successful predictions of old theories. They encompass them. Quantum mechanics didn't prove that classical mechanics was wrong. It showed that classical mechanics is an approximation valid in certain regimes. General relativity didn't prove that Newtonian gravity was wrong. It showed that Newton's theory is an approximation valid at low speeds and weak fields. Whatever new physics we discover, we'll have to do the same thing with special relativity. It will have to explain why special relativity works so astonishingly well in its domain. it will have to reproduce time dilation, length contraction, the relativity of simultaneity, all the phenomena we've tested with extraordinary precision. And the light speed limit is at the heart of special relativity. It's not a peripheral prediction that might be overturned by new physics. It's the central organizing principle of the theory. Any future physics that reproduces relativity's successes will almost certainly preserve the light speed limit in some form. Could there be loopholes, shortcuts, mechanisms we haven't imagined? In principle, yes. I can't rule it out with absolute certainty. But the burden of proof is on those who propose such mechanisms. And so far, every proposed mechanism, warp drives, wormholes, tachyons, everything runs into fundamental obstacles when you work out the details. At some point, you have to make a judgment call. Is it more likely that the universe contains a hidden loophole that happens to violate none of the deep principles we've discovered, or that faster than light travel is simply impossible? Based on everything I know about physics, I believe the latter is far more probable. But I hold that belief humbly. I could be wrong. Science could surprise us. If it does, I'll be the first to celebrate. But until then, I think the responsible position is to accept the most likely truth, even if it's not the truth we'd prefer. Let me turn now to something I've been thinking about a lot: the Fermi paradox and what the impossibility of warp drive might tell us about extraterrestrial civilizations. You know, the Fermi paradox is the apparent contradiction between the high probability that extraterrestrial civilizations exist and the lack of evidence for them. Given the vastness of the universe, the billions of potentially habitable planets, and the billions of years available for civilizations to arise and spread, shouldn't the galaxy be teeming with intelligent life? Shouldn't we have seen some sign of them by now? Many proposed solutions to the Fermi paradox involve the difficulty of interstellar travel. Maybe civilizations arise but never leave their home systems. Maybe the energy and time requirements for interstellar colonization are just too daunting. Maybe the galaxy is full of intelligent species, all confined to their local neighborhoods, all looking up at the same unreachable stars. If warp drive is impossible, if faster than light travel is forbidden by the laws of physics, this makes a lot of sense. Interstellar colonization becomes a multi-generational project requiring enormous resources and commitment. It's not impossible, but it's hard enough that many civilizations might not attempt it or might fail in the attempt. The galaxy might be full of isolated islands of intelligence, each separated by light years of empty space, each aware of the other's existence through radio signals or other electromagnetic emissions, but unable to visit or physically interact. A cosmic archipelago of minds, forever alone together. This is, in a strange way, a comforting thought. It suggests that our situation isn't unique. It suggests that the loneliness we feel when we contemplate the vastness of space is a universal condition shared by every intelligent species that has ever existed. We're not failures for not having conquered the galaxy. We're normal. We're doing what intelligent life does, existing within constraints, reaching out with our minds when we can't reach out with our hands. And maybe, just maybe, that's okay. Maybe intelligence doesn't need to spread across the cosmos to be meaningful. Maybe a single planet, a single civilization, a single moment of understanding in an otherwise unconscious universe is enough. Maybe the value of consciousness isn't measured by how many cubic light years it occupies, but by the depth and richness of its experience. I think about Earth and all the life it contains. Billions of species, trillions of individuals, each with its own form of experience, its own way of engaging with the world. The complexity and beauty here is staggering, and we've barely begun to understand it. Even if we never leave this solar system, There's enough here to explore and appreciate for millennia. The universe isn't diminished by our inability to traverse it. It's still vast, still ancient, still full of wonders. The light from distant galaxies still reaches us, carrying information about cosmic history. The laws of physics still reveal themselves to patient inquiry. The questions still beckon, even if the destinations don't. Now, let me bring this to a close by reflecting on what I think is the deepest lesson here. You know, I've spent my career trying to understand the fundamental structure of reality. String theory, quantum mechanics, relativity, these are attempts to get at the ultimate nature of things, the rules that govern everything. And one thing I've learned is that the universe has a way of frustrating our intuitions while satisfying our deepest curiosities. Quantum mechanics tells us that reality at its core is probabilistic, not deterministic. That seems frustrating. We want certainty, predictability. But it also gives us the extraordinary richness of atomic behavior that makes chemistry possible, that makes life possible. General relativity tells us that space and time are curved, that the geometry of the cosmos is shaped by its contents. That seems frustrating. We want flat, empty space that we can navigate easily. But it also gives us the cosmic evolution that created galaxies and stars and planets, the structure that makes the universe what it is. And now the light speed limit tells us that we can't cross interstellar distances quickly, that the stars are not for us to visit casually. That seems frustrating. We want to explore, to expand, to transcend. But it also tells us something profound about the structure of space-time, about the interconnection of space and time, about the fundamental architecture of reality. Each constraint is also a revelation. Each limitation is also a lesson. The universe isn't saying no to be cruel. It's showing us what it is, what the rules are, how things actually work. And I think there's wisdom in accepting that. Not with resignation, but with understanding. Not giving up on ambition, but channeling ambition toward what's actually possible. Not mourning the loss of warp drive, but appreciating what we have, minds that can comprehend the cosmos, instruments that can probe its depths, theories that can explain its workings. The universe gave us a cosmic speed limit. It also gave us the ability to understand why that limit exists. Both are gifts. You know, I started this journey by telling you that warp drive will never work. And I've spent many thousands of words explaining why the exotic matter, the horizon problems, the causality violations, the quantum instabilities, the deep structural features of space-time that seem to forbid superluminal travel. But I want to end on a different note. Not defeat, but acceptance. Not disappointment, but wonder. The universe is what it is. It's not what science fiction promised us, but it's not nothing either. It's a cosmos of staggering beauty and complexity, governed by laws that we can understand, filled with mysteries we've barely begun to explore. We're tiny creatures on a small planet, looking out at an infinite expanse we'll never fully traverse. And yet, we've figured out the rules. We've traced the cosmic history from the Big Bang to the present. We've deduced the nature of stars, the existence of black holes, the expansion of space, the curvature of space-time. We've reached out with our minds to places our bodies will never go. That's not a consolation prize. That's the main event. That's what it means to be conscious in an unconscious universe, to know, to understand, to wonder. The stars are far away. The journey is slow. Warp drive is a dream that physics won't permit. But we're here. We're aware. We're asking the questions. And in a cosmos that mostly consists of empty space, dead matter, and mindless energy, that's extraordinary. That's unprecedented as far as we know. That's worth celebrating. The universe didn't give us warp drive. it gave us something better. It gave us the ability to understand why warp drive is impossible, and in that understanding to glimpse the deep structure of reality itself. That's enough. That's more than enough. That's everything. Thank you for joining me on this journey through the physics of what's possible and what isn't. From the mathematics of the Alcubierre metric to the philosophy of cosmic humility, we've covered a lot of ground. The stars will remain distant, the light speed limit will hold, but knowledge is its own form of travel, and understanding is its own form of arrival. Keep wondering, keep questioning, keep looking up, because even if we can't go to the stars, we can know them, and knowing them, truly understanding them, is a kind of journey that no distance can prevent. The universe is vast, and we are small, but we are the part of the universe that knows it's the universe. And that, I think, is the greatest adventure of all.